this lecture, we are going to visualize confusion matrix. We will run few lines of the code and investigate every cell in this matrix. Hi everyone, my name is Valentun Sichkar. Let's get started. The objectives for this lecture are as following. You will be able to generate two vectors of classes indexes, one that consists of true classes and one that consists of predicted classes. Display confusion matrix in form of simple two-dimensional NumPy array and in form of beautiful colored graph. Analyze interrelation between classes via confusion matrix. Build classification report and examine different classification metrics. Let's begin. Here are two options: clone or download the code file, or simply code while watching. Find the link in the description. Pause video and come back when you are ready. We will code in Jupyter Notebook. Let's jump to the programming environment. We are going to visualize confusion matrix. Algorithm is as following. Firstly, we generate two vectors, true one and predicted one. Next, we display confusion matrix as simple two-dimensional NumPy array and in a more convenient way as colored graph. After that, we build table with classification report. As a result, we will have image with confusion matrix and table with classification report. We will analyze these results in deep details. Let's go through the code. In this cell, we import minimum needed libraries. To plot results, to process arrays by NumPy library. We also import from scikit-learn library functions to build classification report, to build and display confusion matrix. We will consider these new functions in details in a few moments. Let's run this cell. Okay, let's continue. In the next cell, we prepare list with labels for our imaginary model. We decide that we want to have 5 classes to be analyzed via confusion matrix. Later, you can experiment and apply different number of classes for your own model. Let's run this cell. Okay, let's continue. In this cell, we generate true vector that holds correct class numbers for our imaginary dataset. We do it by NumPy function np_random_rand_int. As arguments, we pass lowest number of the class, that is 0, and highest number of the class that we obtain by getting length of the prepared list with classes names. We also set total number of samples for all classes in our imaginary dataset as 100. Later, you can experiment and set here different number. Last argument specifies type of the generated numbers. We set it to integer type as classes numbers must be integers. Let's run this cell. We can see generated vector that consists of correct true classes numbers for our imaginary model. Pay attention. Your values here will be different due to used function random. When you use not imaginary but real model, you will initially have predefined correct classes numbers inside real dataset. Okay, let's continue. In the next cell, we print distribution of samples among classes for our imaginary dataset. To calculate number of images for every class, we use NumPy function np_unique. As argument, we pass yTrue NumPy array that includes classes numbers. The function will calculate how many times every class number is met in this array. We also activate here argument return counts that will actually return calculated frequency for every class. Results will be written into two variables. First one, classes indexes, will keep sorted unique classes numbers taken from yTrue array. We have 5 classes, then these numbers will be from 0 to 4. Next variable, classes frequency, will keep frequency for every class. Let's run this cell. We can see here unique classes numbers and their frequencies. In other words, number of samples for appropriate class. When you use not imaginary but real model, you will have here distribution of images among classes inside real dataset. Okay, let's continue. In this cell, we plot histogram to show distribution of samples among classes. Here we define default size of the plot, figure object, and plot bar chart by plt bar function. As first argument, we pass sequence of scalars that are coordinates for every bar along x-axis. In our case, it is numbers from 0 to 4. As second argument, we pass height for every bar. In our case, it is frequency for every class. Next, we specify type of alignment for every bar, that is center. It means that every bar will be aligned according to its x coordinate. The last argument is opacity of bar chart. We set it to 0.6. Here we set names to axes. And here, instead of just showing class number for every bar, we set labels by function pltxticks. As arguments, we pass locations of ticks on the plot along x-axis and corresponding list of classes names that we defined earlier. Finally, we set title to bar chart and save it into a file. To show bar chart, we call function pltshow. Let's run this cell. We can see bar chart that visualizes frequency for every class. Okay, let's continue. In the next step, we generate second vector that holds predicted classes numbers for our imaginary dataset. Firstly, in this cell, we make a copy of previously generated true vector. We do it by numpy function npcopy. It will give us a complete copy of array and not just a reference to the true array. By doing so, we make sure that all changes we apply to this new variable with numpy array will not influence the same numpy array in true variable. Find more details and examples by the link at the end of this Jupyter notebook. Let's run this cell. Okay, let's continue. In the next two cells, we slightly change our vector with predicted classes numbers in order to include inside it some error. In this cell, we randomly choose indexes to be changed. We again apply numpy function np_random_randint. As arguments, we pass lowest index, that is 0, and highest index that we obtain by getting length of the defined vector with classes numbers. By the next argument, we set total number of indexes to be chosen. Our imaginary model has 100 samples, and by multiplying this number on 0.25, we get 25 randomly chosen indexes. These indexes we will use in the next cell to change true classes numbers to different, in other words, not correct classes numbers. It also can be seen as accuracy of the model, where approximately 75% of samples are classified correctly and 25% classified incorrectly. Later, you can experiment and set here different number, bigger or smaller. We also make the resulted size as integer number in case we get here float value. Let's run this cell. We can see 25% of chosen indexes that we are going to use in the next cell. Pay attention, your values here will be different due to used function random. Okay, let's continue. In the next cell, we take randomly chosen indexes and by this for loop, one by one, access classes numbers by these indexes in predicted vector. After we get access to class number, we change it by randomly choosing new different class number. One more time, we apply here NumPy function np_random_rand_int, specifying low and high values. We do not specify here argument size, as we need just one resulted number. Generated new class number we save into the same position in predicted vector according to current index. By this checkpoint, we print current index, correct class number located by the current index, and generated new class number for the current index. We apply function format to the string with needed text. In the curly brackets, we set odd number of arguments that are passed to the function. We have here 3 arguments. That's why we specify in curly brackets 0, 1, and 2. For the first argument in the curly bracket, we also specify 2d after colon. It means that we want to allocate for decimal numbers 2 positions. For example, numbers that are in range between 10 and 99 already have their 2 positions, but numbers that are in range 0 and 9 have only 1 position, and therefore, before such numbers will be added a gap. It is needed just to align output rows from this cell and better see the results. Okay, let's comment this line of the code and run this cell. Here it is. We can see classes indexes and correspondent classes numbers in both vectors, true and predicted. For now, they are the same. Let's uncomment this line of the code and run this cell again. We can see that classes numbers inside predicted vector were changed. However, pay attention here. Some classes numbers were again generated to the same values. Therefore, the accuracy of our imaginary model will be slightly above 75%, as not all 25% of predicted classes numbers were changed. Your values here will be different due to used function random. When you use not imaginary but real model, you will have, after training, your own predicted vector. Okay, let's continue. In the next step, we compute and print confusion matrix in form of NumPy array. We use scikit-learn function confusion matrix, passing as arguments correct true class numbers and predicted class numbers. Let's run this cell. Confusion matrix visually represents correct and incorrect predictions by following calculated 4 numbers: true positive, false positive, true negative, and false negative. Each column represents an index of predicted class. Each row represents an index of correct class. The diagonal of the matrix holds true positives that are numbers of correct predictions for appropriate classes. Columns represent false positive cases, and rows represent false negative cases. Before we consider in details one particular class, let's move on to the next cell and display confusion matrix in a more convenient way. In this cell, we display confusion matrix by this function of scikit-learn library. We pass as argument NumPy array of computed confusion matrix in the cell above and specify labels to be shown instead of classes numbers. Result we return into new variable that is object of the plot. By applying method plot to the object that holds our confusion matrix, we set color map and rotation angle to the labels along x-axis. We apply rotation angle in order to fit labels on the plot and make them not overlap each other. We will see it in a few moments. Later, you can experiment and choose different color map and different rotation angle. To print full list of options for color maps, run one of the cells at the end of this Jupyter notebook. Next, We set font size for labels along Y and X axis, give title to the plot, save image of confusion matrix into the file, and show the plot. Let's run this cell. We can see graphical representation of confusion matrix. Let's do one more step before we analyze this confusion matrix. Let's move to the next step, discuss definitions, and build classification report. In the next step, we build classification report. We use here scikit-learn function classification report, passing as arguments correct true classes numbers and predicted classes numbers. Let's run this cell. We can see here accuracy of our imaginary model. This accuracy is also called as global accuracy, but it doesn't consider disbalance of samples in every class. That's why we have here other metrics that are calculated differently and take into account number of images in every class. Let's now discuss definitions. True positive, false negative, true negative, and false positive represent 4 ways to check if the predictions are correct or incorrect, and they are used to calculate these metrics of the classification report. When we feed our input image to the neural network, we ask the network a question: what do you see? And neural network has to decide to which class input image belongs to. We know the correct true class number of the input image, and we will know the answer from the network. By the help of these indicators of the classification report, we can evaluate how good is our model. True positive represents a number of images with right predictions when label is true and classified as true. False negative represents a number of images with not right predictions when label is true but classified as false. True negative represents a number of images with right predictions when label is false and classified as false. And finally, false positive represents a number of images with not right predictions when label is false but classified as true. Precision answers following question: what percent of the predictions did the model identified as correct? In other words, it shows ability of the model not to label an image as positive that is actually negative. Precision is defined as the ratio of true positives to the sum of true positives and false positives. Recall answers following question: what percent of the correct predictions did the model catch? In other words, it shows ability of the model to find all positive samples. Recall is defined as the ratio of true positives to the sum of true positives and false negatives. F1 score metric is another measure of the model's accuracy. It is also called as weighted harmonic mean of the precision and recall, because it takes into consideration these two metrics, and the contribution of precision and recall are equal to F1 score. F1 score is calculated by following equation. In the classification report, we also can see column with name support. It represents number of samples for every class. We also calculated it in one of the cell above. For example, for the first class we have 16 samples. For the second class we have 20 samples, and so on. We also can see in classification report summary rows with macro average and weighted average. Macro average calculates the mean of the metrics giving equal weight to each class. For instance, macro average of the first column, that is precision, is calculated as following, but weighted average of the same column is calculated as following. It takes into account imbalance of number of samples for every class. Okay, let's come back to the confusion matrix. As we already discussed, columns represent predicted labels and rows represent correct labels. Diagonal represents true positives for appropriate classes. Let's consider first class. As can be seen, number of true positives is 12. However, if we look back at classification report and find their column support, we can see that total number of images for the first class is 16. It means that rest of the images were misclassified. For example, in this row that represents false negative cases, 2 images of horses were classified as cats. Another 1 image of horse was classified as dog, and 1 more image of horse was classified as polar bear. False negative cases in this row represent number of misclassified images that are actually true for this class, but predicted as false. When our model sees only images with horses, consequently in these cells values must be 0, but model, for some cases, failed to recognize this condition. If we sum all numbers in the first row, we will get total number of images with horses in our model. In this column that represents false positive cases, 2 images of tigers were classified as horses, and 1 image of dog was classified as horse. False positive cases in this column represent number of misclassified images that are actually false for this class, but predicted as true. For example, when our model sees other images than horse, consequently in these cells values must be 0, because horse can't be as tiger, cat, dog or polar bear. But model, for some cases, failed to recognize this condition. Rest of the area for the class horse is considered as true negative cases. The same analysis can be done for other classes: tiger, cat, dog, polar bear. If we consider class cat, we can see number of true positive cases, that is number of correct predictions. But if we look back at classification report and find their column support, we can see that total number of images for this class is 17. It means that 1 image was misclassified. In this row that represents false negative cases, 1 image of cat was classified as polar bear. False negative cases in this row represent number of misclassified images that are actually true for this class, but predicted as false. When our model sees only images with cats, consequently in these cells values must be 0, but model, for one case, failed to recognize this condition. If we sum all numbers in this row, we will get total number of images with cats in our model. In this column that represents false positive cases, 2 images of horses were classified as cats. 1 image of dog was classified as cat, and 1 image of polar bear was classified as cat. False positive cases in this column represent number of misclassified images that are actually false for this class, but predicted as true. For example, when our model sees other images than cat, consequently in these cells values must be 0, because cat can't be as horse, tiger, dog or polar bear. But model, for some cases, failed to recognize this condition. Rest of the area for the class cat is considered as true negative cases. In ideal situation, when our model has 100% of accuracy, we could see here in the diagonal only true positive cases, and rest of the confusion matrix would be 0. Anyway, by the help of confusion matrix, we can visually analyze misclassification. This color bar shows how close one particular cell is to the maximum value. Color intensity of the cells also helps visually to analyze confusion matrix. At the end of this Jupyter notebook, you can find some useful comments. To get help information, just run these cells. In this lecture, you obtained new skills. We successfully generated two vectors with classes indexes, true one and predicted one. You are able now to produce vectors and apply them to represent classification results. We also displayed confusion matrix and built classification report. You are able now to illustrate interrelation between classes via confusion matrix and interpret different classification metrics. Code that we ran in this lecture you can modify and apply to your own project. Use this code as template, implement needed modifications, and apply it to any other project you have. Do you want to build your own deep classification model? Then join the course. Find the link below this video. You will be able to design your own deep CNN model for classification tasks, train and test this model on image and in real time by camera, build your own classification report and analyze confusion matrix. Click the link below to start now. Thank you very much for watching. Please be sure to like this video and subscribe to the channel if you haven't already. See you soon in the next lectures.